You think you understand the speed of light, 299, 792, 458 meters per second. Fast, really fast. The fastest thing in the universe. But here's what they don't tell you. The speed of light isn't just a speed. It's not even about light, really. It's the structure of reality itself, woven into the fabric of space and time in a way that makes going faster literally impossible. Not difficult, not impractical, impossible. And when you dig into why, when you really ask what stops you from breaking this barrier, you discover something so strange, so fundamentally alien to everyday experience, that it changes everything you thought you knew. Most people just accept it. Einstein said so. Speed of light is the limit. Done. But that's not an answer. That's just repeating words. So let me ask you this. What actually stops you? What invisible wall slams down when you try to go faster? The answer is going to blow your mind. But to get there, we need to start somewhere unexpected. We need to start with the moon. Let's talk about something simple, something everyone knows. Things fall. Drop a ball, drop a rock, drop your phone if you're brave enough. They all fall down. And if you measure it precisely, which took centuries to do accurately, you'll find that in 1 second, they fall exactly 16 feet. Galileo figured out the principle using inclined planes, because timing a 1 second drop was impossible back then, every time. Predictable, consistent. Now look up at the moon. It's just sitting there, orbiting, going in circles, not falling. Or is it? Here's where things get interesting. What if the moon is falling? Think about it. If the moon were stationary, just hovering in space, what would happen? Gravity would yank it straight down toward Earth. No question. But the moon isn't stationary. It's moving sideways, tangent to its orbit at thousands of miles per hour. So while gravity pulls it down, the moon keeps missing the Earth. It falls toward us, but never hits. That's what an orbit is. Continuous falling while moving sideways fast enough to keep missing. Now, Isaac Newton, brilliant, obsessive, probably a little strange. He had an idea. The moon is 240,000 miles from the center of the Earth. We're standing on the surface, 4,000 miles from the center. So the moon is 60 times farther away than we are. Newton asked, what if gravity gets weaker with distance? Not just a little weaker. What if it follows a precise mathematical rule, an inverse square law? That means if you go twice as far, gravity becomes 4 times weaker, 3 times as far, 9 times weaker. If that's true, then at the moon's distance, 60 times farther, gravity should be 60 squared times weaker. That's 600 times weaker. Now here's the crazy part. On Earth, gravity accelerates things at 16 feet per second squared. That's how much speed they gain each second. If gravity at the moon is 600 times weaker, then the moon's acceleration toward Earth should be 16 feet divided by 600, about 0. 1,044 feet per second squared. In 1 second, that means the moon falls about 1/20th of an inch toward Earth. Newton calculated this. And when he checked against observations, perfect match. The moon was falling at exactly the rate Newton predicted. This wasn't just a theory. This was a prediction. Newton took 2 completely independent facts, how fast things fall on Earth and the moon's orbit, and connected them with one law, the law of gravitation. There was no going back. But Newton didn't stop there. He calculated what the shape of planetary orbits should be if gravity follows an inverse square law. And he found ellipses. Guess what? Planets do move in ellipses. Johannes Kepler had already measured that decades earlier, but Kepler didn't know why. Newton explained it. He got 3 for the price of 2. Then more things started falling into place. The tides, for example. Why are there tides? Because the moon pulls on the Earth. Simple, right? But hold on. If the moon just pulls the Earth toward it, there should only be 1 high tide per day, the bulge of water on the side facing the moon. But there are 2 tides every day, every 12 hours roughly. Why? Some people thought the Earth was pulled away from the water. Others thought the water was pulled toward the moon. Both were sort of right. Neither got it completely. Newton figured it out. The water on the near side is closer to the moon than the Earth is, so it gets pulled more. The water on the far side is farther from the moon, so it gets pulled less. Two bulges. One where water is pulled harder toward the moon. One where water is left behind because the Earth itself is pulled more. 2 tides per day. And suddenly, all kinds of things made sense. Why the Earth is round? Because gravity pulls everything inward. Why it's not perfectly round? Because it's spinning. So the equator bulges out slightly. Why the sun and moon are round? Why the planets move the way they do? One law, gravity. And it explained everything. But here's where the story takes a strange turn. Because as science developed, as measurements became more precise, people started testing Newton's law even more carefully. And they found a problem. The first really careful tests involved the moons of Jupiter. Astronomers observed them over long periods, tracking their orbits with incredible precision. And according to Newton's laws, they should have been predictable down to the second. But they weren't. Sometimes the moons appeared 8 minutes ahead of schedule. Sometimes 8 minutes behind. 8 minutes, that's huge. Something was wrong. Was Newton's law broken? Not so fast. A Danish astronomer named Ole Armer noticed something odd. The moons were ahead of schedule when Jupiter was close to Earth, and behind schedule when Jupiter was far away. Rather peculiar. Armer had an idea, a wild idea. What if light takes time to travel? What if when you look at Jupiter's moons, you're not seeing them as they are, but as they were some time ago, depending on how long it took the light to reach you? When Jupiter is close, the light arrives faster. When Jupiter is far, it takes longer. So Arve corrected the observations for the time delay of light traveling across space, and suddenly the discrepancy vanished. The moons were exactly where Newton predicted. The law of gravitation was fine. But now, for the first time, we knew something new. Light is not instantaneous. It travels. It takes time. And Armer calculated its speed. Think about what just happened here. We found the speed of light, not by measuring light directly, but by having confidence in the law of gravitation. When something didn't match, instead of throwing out Newton's law, Armer said, what if there's another phenomenon at play? And he was right. This is how science works. When one law is solid, you can use it to discover another one. Each new discovery becomes a tool for even more discovery. An avalanche, and it's been going for 400 years now. We're still avalanching along at high speed. But here's the thing. Once you know the speed of light, once you measure it, you start noticing something very, very strange. Light always travels at the same speed. Always. No matter who measures it, no matter how fast you're moving. Let me make this concrete. You're standing still. You shine a flashlight. You measure the speed of the light coming out. 458 meters per second. Fine. Now you get on a train, a really fast train, moving at, say, half the speed of light. You shine the flashlight forward, in the direction the train is moving. Common sense says the light should now be traveling at the speed of light plus the speed of the train. Just like if you throw a ball forward from a moving train, the ball moves faster than if you threw it while standing still. But that's not what happens. You measure the light, still 299, 792, 458 meters per second. Exactly the same, you think. Okay, maybe I measured wrong. So you get the train going faster. 90% the speed of light. You shine the flashlight forward again. Still the same speed. You get frustrated. You push it to 99.999% the speed of light. You shine the flashlight. You measure. Still the same speed. The speed of light does not add. It doesn't combine with your speed. It's always the same. No matter how fast you're moving, this should break your brain. This is not how speeds work in everyday life. Speeds add. If you're on a train moving at 50 mph and you walk forward at 3 mph, you're moving at 53 mph relative to the ground. But light doesn't do this. Light always moves at the same speed relative to you, no matter how fast you are moving. Why? Einstein figured it out, and what he discovered is so strange, so contrary to common sense, that even now, over a century later, people struggle to accept it. Time and space are not fixed. They're flexible. They bend. They stretch. They compress. And they do this to keep the speed of light constant. When you move faster, something strange happens. Other observers measure your clock as ticking slower. From your perspective, everything feels normal. Your time passes normally. But someone watching you go by sees your clock running slow. Both perspectives are equally valid. That's relativity. And distances contract. But again, it depends on who's measuring. If you're moving fast, you measure the distance to your destination as shorter. Then someone at rest would measure it. Space itself isn't compressed. Measurements of space depend on relative motion. These effects are real. They're not optical illusions. They're not measurement errors. Time actually slows. Space actually contracts. And the amount they change is exactly the right amount to make the speed of light come out the same for everyone. Let me say that again, because this is where everything we think we know about reality starts to fall apart. The universe adjusts time and space, bends them, stretches them, compresses them, to ensure that light always travels at the same speed for everyone. The speed of light is not just a speed. It's a structural constant of the universe. Space and time are arranged in such a way that this speed is the same for everyone, always. Now here's where it gets even stranger. If you try to accelerate something, anything, to the speed of light, something very weird happens. The closer you get to the speed of light, the harder it becomes to go faster. It's not that you run out of fuel. It's not that your engine isn't strong enough. What's really happening is this. As you go faster, your momentum increases faster than your velocity at low speeds. Momentum equals mass times velocity. But near light speed, the momentum grows much faster. It approaches infinity as you approach light speed. This isn't because your mass increases. Mass stays the same, but the relationship between velocity and momentum changes. It becomes exponentially harder to accelerate you. And as you approach the speed of light, that momentum approaches infinity. To actually reach the speed of light, you'd need infinite energy, which is impossible. So nothing with mass can ever reach the speed of light. Not because of some arbitrary rule, not because of engineering limitations, because the structure of space-time itself prevents it. Light can travel at that speed because photons have no mass, zero. Massless particles can travel at the speed of light. In fact, they must. They have no choice. But anything with mass, you can get close. Very close, 99.9999% of the speed of light, but never quite there. The universe won't let you. Now you might ask, but why? Why is the universe set up this way? Why is there a speed limit at all? Here's the answer that's going to frustrate you. There isn't a deeper why. The speed of light isn't a speed limit imposed on the universe. It's a consequence of how the universe is structured. Space and time are not separate things. They're woven together into space-time. And space-time has a geometry, a structure. And that structure has a built-in conversion factor. Between space and time, that conversion factor is the speed of light. It's not that light is special. It's that space-time has a maximum rate at which cause and effect can propagate. Light happens to travel at that rate because light has no mass. But the rate itself, that's a property of space-time, not of light. If light didn't exist, the speed limit would still be there. It's a feature of the universe itself. Here's one way to think about it. It's an analogy, not the full picture, but it helps. You're always moving through space-time, and there's a sort of total motion. That gets divided between space and time. When you're still in space, all that motion is through time. When you move through space, you divert some of that motion away from time. It's not perfectly rigorous, but it captures something real about how space-time works. If you're sitting still, you're moving into the future at maximum speed, 1 second per second. But if you start moving through space, you have to divert some of that motion away from time. You're now moving through space and time, which means you're moving through time more slowly. The faster you move through space, the slower you move through time. And there's a maximum. Here's something strange. There's no valid photon's perspective in relativity. You can't construct a reference frame moving at light speed. The math completely breaks down. But we can say this. For anything moving at light speed, the time dilation factor becomes infinite, which is why massless particles must travel at this speed, and only this speed. You can't go faster than light, because you can't have less than zero motion through time. That's the limit. That's the wall. And here's the beautiful part. This isn't just theoretical. We've tested this over and over and over. Particles and accelerators get accelerated to 99, on 99% the speed of light. And guess what? The closer they get, the harder it becomes to accelerate them further. Exactly as predicted. GPS satellites, they have to account for time dilation. Actually, two kinds. They're moving fast, which makes their clocks run slower. That's special relativity. But they're also in a weaker gravitational field, which makes their clocks run faster. That's general relativity. The gravitational effect wins. So overall, satellite clocks run about 38 microseconds faster per day than ours. If we didn't correct for this, GPS would be off by miles, muons. Subatomic particles created in the upper atmosphere by cosmic rays. They should decay before reaching the ground. Their lifetime is too short, but they're moving close to the speed of light, so time slows down for them. From their perspective, they live long enough to reach the ground. From our perspective, they live longer because they're moving fast. Either way, more muons reach the ground than should, exactly as relativity predicts. It's not speculation, it's measured, tested, confirmed. The speed of light being a limit is as well established as anything in physics. So let's bring this all together. Why is the speed of light the limit? Because space-time is structured in a way that has a maximum rate of cause and effect. That rate is the speed of light, not because light is special, but because space-time itself has this built-in conversion factor between space and time. You can't go faster, because going faster would require moving backwards in time, which doesn't make sense. You can't have negative time. You can't undo cause and effect. The speed of light is the speed at which now propagates through the universe. It's the speed at which information can travel, the speed at which forces act, the maximum rate of change. And this whole journey, this avalanche of discoveries, started with Newton figuring out gravity by watching the moon, then Armour figuring out the speed of light by watching Jupiter's moons, then Einstein realizing the speed of light is constant and deriving relativity from that, then thousands of experiments confirming it, each discovery building on the last, each new insight cracking open doors to even stranger questions. That's how science works. That's the avalanche that's been going on for 400 years. And we're still avalanching along at high speed. The speed of light isn't just a number, it's the key. It's the thing that unlocks how space and time work. It's the thing that shows us reality is weirder than we thought, and somehow more beautiful because of it. And the fact that we can understand it, that we can measure it, test it, use it to make predictions. That's the beauty of physics. Not comfort, not simplicity, truth.